So we've all seen the gradient descent equation. This is the algorithm we use to find a set of parameter values that minimize our loss function. But there's still one important question. Where does this gradient vector actually come from? How do we actually calculate all these partial derivatives? The answers largely come down to the most important thing known in calculus, the chain rule. Let's see how it's used in machine learning. Here's our binary cross entropy loss function that we'll use for this episode. Our goal is to compute its gradient with respect to our parameter vectors theta. So naturally the first thing we might do is differentiate this equation. But there's a problem. If you look carefully, theta doesn't actually appear anywhere in the equation. So how can you differentiate something with respect to something that isn't even there? Well, the answer is that theta is there, it's just hidden. Remember how logistic regression works. For each training example, the individual loss is that on the board. Still no theta, but what exactly is p? It's the output of our sigmoid function. P is equal to sigmoid of z. And what is z? Z is x transpose theta. So the loss doesn't depend on theta directly. Instead, changing theta changes z. Changing z changes the predicted probability p. And changing p changes the loss. So if you look at this dependency diagram, that's the path that connects our parameters to the loss. And because the effect of theta has to travel through multiple functions before reaching the loss, this is exactly where the chain rule comes in. So let's see how this works. Since the total loss is just the average of all individual losses, let's first understand how to differentiate one training example. So a reminder of the chain rule, I've written it on the board. So let's work out dl by dp. So log of p differentiates to 1 over p, and you're multiplying it by minus y, so it's minus y over p. Log of 1 minus p is minus 1 over 1 minus p, and it's minus 1 because the derivative of our inner function is minus 1. So that part becomes minus minus bracket 1 minus y over 1 minus p. So dl by dp is minus y over p plus 1 minus y over 1 minus p. And then we can combine the fractions into one denominator and we get p minus y over 1 minus p. Cool. The next step is to take the derivative of the probability function with respect to zi. So p of I, remember, is the sigmoid of zi, and the derivative of the sigmoid is p 1 minus p. So to show you why that is, again, we're just applying the chain rule. The minus 1 comes down, the 1 plus e to the power of minus z is to the power of minus 2 now, and the derivative of the inner function is minus e to the power of minus z. So after simplification, you're going to get e to the power of minus z over 1 plus e to the power of minus z squared, which can also be written as p 1 minus p. And now finally, dzi by d theta is just x. So the gradient becomes 1 over m, summed from 1 to n, p of I minus y of I, all of that multiplied that by xi. Or to put that into more linear algebra form, the nabla j theta is equal to 1 over m x transpose multiplied that by p minus y, where x includes the one column for the bias and the features data themselves. So we've now built the entire logistic regression mathematical principles from scratch. We started with probabilities, we derived the binary cross entropy loss, we learned how gradient descent updates our parameters, and today we've discovered where that gradient actually comes from. That's one complete machine learning algorithm built from first principles. But ladies and gentlemen, the journey doesn't stop there. There are many more machine learning algorithms left to explore. And as you'll soon discover, many of the mathematical ideas we've learned in these last few episodes will continue to appear again and again and again. So if you are interested in content like this, make sure to like, comment, share, and subscribe. I'll see you in the next one.